What's up, ACT Samurai? Today we're taking a look at probability. Probability on the ACT they'll give you three situations. They'll come at you with three different attacks, and I'm going to show you the defenses for each of those attacks. The first situation that you'll be presented with is one I think is very common and very easy to approach, even if you're not familiar with probability, and that's the bag of marbles question. So the question usually says, you have a bag of 10 marbles, 5 of them are blue, and 3 of them are yellow, and 2 of them are red. And the question says, what are the odds that you'll get a blue one if you pull a marble out of the bag? So you say, alright, we have 10 total marbles, and we have 5 chances of getting a blue marble. So your odds are 5 out of 10. So that simplifies to 1 out of 2, and that's your answer. The second situation is the technical term, a probability distribution table. If that sounds scary, forget it. I'm just going to show you the move that you need to know for the test. So the move goes like this. You have 2 columns of data. The first column is just a bunch of numbers like that, and the second column is another group of numbers. It's going to be like 0.1, 0.75, 0.9, and 0.32. And what the ACT will expect you to know how to do is to multiply across and then add it to the next one. So we're going to multiply 0 times 0.1 and add it to the next one, 1 times 0.75. And then we do the whole thing. We multiply everything out. So 2 times 0.9 plus 3 times 0.32. You add those all up together, and that's usually your answer. They come at you, as always, with different looks about that question, but at its core, that's what you have to do. Not too bad, right? The third situation, and this is the most rare. Here's what you have to do. You have to memorize these 2 formulas, and then on the test, they might ask you to recite the formula, and then you're just good to go. You just circle the answer with the formula. So the 2 formulas that I'm talking about are this one right here. One is the probability that A and B occur. So this is like, what's the probability of your mom buying pizza and buying ice cream for dinner? It's the probability of A and B. Alright, so this is calculated by doing P of A times P of B. There's a second formula, which is what is the probability of A or B happening? And that's equal to this formula. So P of A plus P of B minus P of A times P of B. Running out of space. So if you memorize those formulas, you might be asked a question to recite them, and you'll get the answer right away. If you want more information about them, go ahead and check out online. Just search probability formulas, and I'm sure you'll get plenty of good information. Alright, let's jump into the practice problems. This is where the money is made, right? So a bag contains 10 pieces of flavored candy. 4 lemon, 3 strawberry, 2 grape, and 1 cherry. 1 piece of candy will be randomly picked from the bag. What is the probability that the candy picked is not grape? So we had 2 grapes, right? We had 2 grapes. So what are the odds that we get any one of the others? It's going to be 4 plus 3 plus 1 over 10. Right? Any one of the others, lemon, strawberry, I forget the last one, over 10. And that's going to be equal to 8 over 10, which simplifies to 4 over 5. So E is our answer. Here we have a second version of the same kind of problem. So I want you guys to pause the video and try it out. I'm going to solve it right now. We have a 13-member math club, so there are 13 members, and they need to choose a student government representative. They decide that the representative who will be chosen at random cannot be any of the officers. There's 3 officers of the club. What is the probability that Samara, who is a member of the club but not an officer, will be chosen? So there are only 10 eligible members, right? Because 13 minus 3 officers leaves 10 eligible members for the position. Samara is one of the 10. So what are her odds of being chosen? It's going to be her out of 10, right? I can confirm that's correct. I just looked up the answer, so it is in fact 1 out of 10. That's as simple as it gets. So the third problem is not a probability problem. In fact, we're not going to do this problem, and I apologize if you can't satisfy, if that leaves you, it leaves your curiosity unsatisfied. So I just wanted to point out that it's not a probability problem, but it's masquerading as one. So it says here, what is the probability P? What value is closest to the probability that blah, 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 blah. I just wanted to show you that sometimes the ACT masks their problem. So the way you solve this one is by plugging in numbers, and it's really not hard at all. It's a very simple problem, but not a probability one. So keep an eye out. Keep your thinking cap on. This is situation number 3. So I talked about memorizing the formula. Here's where this pays off. So this question basically asks you, what is the formula for probability of A and B occurring? And the answer is P of A times P of B. So your answer is D. Ignore all the mumbo jumbo, right? They make these questions so long, and it's never that hard. Here's the second kind of probability problem, and this one's really common. So let's go ahead and just note one thing before we get started, which is that you have 2 columns of data right here, right? So what are we going to do? Remember the move. We take the value over here and we multiply it to this value, 0.6 times 0.2, and then we add that to every other value on this table. So we're going to do the same thing for each one of these. Now, before I actually solve this, let's go ahead and read the problem and see if we can understand it. A certain hotel room has 80 rooms. Based on many previous years' occupancy rates, the owner of the hotel constructed the table below showing the daily occupancy rates of their probabilities of occurring for the coming summer season. Based on the probability distribution in the table, to the nearest whole number, what is the expected number of rooms that will be occupied on any given day during the coming summer season? So let's analyze this. We have 80 rooms. There is a 20% chance that 60% of those will be occupied. If that seems like a lot to juggle in your head, it totally is. So I'm just going to show you what that means. That means there's a 20% chance that 60% of the rooms will be occupied. But we have to add that to the 40% chance that 70% of the rooms are occupied. And then we're going to add that to the probability, the 30% probability that 80% of the rooms are occupied. And lastly, we're going to add that to 10% probability that 90% of the rooms are occupied. When we add all of these up, multiply it out, add them up, you get 0.12 plus 0.24. I'm sorry, that's actually 0.28 plus 0.24 plus that's going to be 0.09, right? And we get 40, this is 52, right? 52 plus 0.09 is 61. 61 plus 0.12 is 73.73. So 73% of the rooms on any given day will be filled. So let's multiply that times 80, because what they asked, what is the expected number of rooms? They didn't ask for the percentage, they asked for the number of rooms. So we're going to use 80 and multiply it times the percentage we found. That's going to be 0, and then 8 times 3 is 24. 8 times 7 is 56, plus 2 is 58. So 58.4 rooms are expected to be filled, which is C. We have another similar problem. Now, they say machine A is going to produce some defective springs. It might produce 0, it might produce 1, it might produce 2 or 3 defective springs any given day. Now, the probability of each of those occurring are over here. So let's go ahead and find out which, what do they want? They want the number of defective springs produced by machine A in any single day. Okay, so let's go ahead and start multiplying this out. And we get, go ahead and calculate this if you haven't already. Plus 0.2 is 0.45. So 0.45 springs every day is going to be defectively produced. Not too bad, right? Not too bad. Let's go ahead and take a look. I believe there are two more. So let's I'm going to let you guys try to solve this one out. The probability distribution of the discrete random variable x is shown in the table below. What is the expected value of x? What do you think we do? Let's go ahead and multiply across and add them all together. So clearly it's 2 plus all this nonsense. So clearly it's more than 2. It has to be 3 and 1/6. I'm sure if I found common denominators, I would get 3 and 1/6. But I'm just going to skip ahead because you guys get the idea. Now this last problem is the same thing, but they do a little bit of a twist. So let's go ahead and take a look at this one. So let's check it out. For each of the first 5 possible values of x, the table below gives probability p of x that a certain factory machine will make x errors on any given workday. Yeah, alright, we have our 2 columns just as we're used to. Which of the following values is closest to the probability that this machine will make at least 1 error on any given workday? Now I haven't emphasized, like I normally like to do, the details, right? The detail here is that it's making at least 1 error. So we're only looking at these values, right? Only these errors. So let's calculate that. So it's going to be 1. Once you add those together and multiply them out, you get k, 0.19177. Alright guys, let's go ahead and review just some of the things that we saw. We saw that there were marbles in a bag. In our case, we were given candies in a bag, but it was basically the same problem. And that was the first situation that we saw. It's a fairly common situation. The second situation we saw was this probability distribution table. And all you had to do for most of them was multiply across and add them up. Not too bad, right? The last situation we saw was a memorization question where it just said, please recite this formula. And if you memorize them, then you're good to go.